Hello everyone. Um, Greetings. I'm not going to take too much time to introduce because I will let Keon introduce himself. Just to say that we are super excited for this lecture. Keon, I think, is one of the two or three only instructors who has been around for every single PBA opportunity that we've had. Um, Correct me if I'm wrong, Keon, but I'm pretty sure you've been at all
Yeah.
in-person waves and you've also been involved in the creation of the PBA-X content. Um, and we love having him around. We will take him for as long as he wants to give us his time. So we are super excited that he has agreed to talk to you all today. Um, it's just you, yeah. And I am recording, so if you do not want, I'm not sure if you'll be able to see your faces on the recording, but if you want to make sure that you're not on the recording, go ahead and turn off your camera now. And I will let Keon get us started. Keon, go ahead and make sure you introduce yourself to everybody.
Yes. Thank you for the kind words and the introduction. I'm always happy to be part of PPA, and it's been indeed an honor and my pleasure to be part of the first five cohorts, the original PBA and now PBA-X and soon PBA Campus. Um, Maybe I can go to my introductory slides, a few words about myself. So my name is Kian. I'm originally from Iran. I moved to Amsterdam at some point, and nowadays I live in Lisbon. Usually in the digital world, my username is Kian Enigma. There's nothing enigmatic about me. I'm sorry. It's like a silly username that just stuck with me throughout the years, and I never bothered to change it. I'm an engineering lead at Verity Technology and also part of the Polkadot Core Fellowship. You can find the slides and some of my other blog posts and stuff also on my website. I always put any kind of like public speaking that I do in there for reference, so you can find these slides there. Also about the setup of this presentation. So as you know, the lecture is about smart contracts. It'll be high level. Feel free to raise your questions as I'm presenting in the chat. At some point, either Aaron would ask me to answer them or I would check them myself. If not, at the end, we'll have Q&A. Also about the setup here, unfortunately, my main monitor is in front of me, but my camera is there. So I apologize that I'm not most of the time looking at all of you, but yeah, it's just the setup is not optimized for that. Okay, I think with that, I can get started about smart contracts. So I want to start with a building a mental model about what blockchains are. So before we go into smart contracts, and there's a couple of popular models out there that people refer to, and I have opinions about them, and I would like to share that. And then we're going to stick to one of these mental models for the rest of this lecture. So something that's thrown out there quite a lot, and I personally really dislike it, is that a blockchain is just a database. It's just somewhere that you can store data. For a number of reasons, I think this is a very bad mental model. I think it undervalues what blockchains can do, and it's like just too simplistic. It's one of those mental models that's been out there for such a long time that you probably hear it a lot. It's kind of hard to get rid of it, but I personally don't like to stick to it. A little bit more formal and mathematical, blockchains are very often represented as state machines. State machines are a term in computer engineering, computer science, which represents a system that has a current state and through a mutation can go to a new state. And this is very accurate and actually correct. But for simplicity, I also don't like this, as in like it's not as simple as I wish it to be. The model that I use these days to describe blockchains, I think it's good in that it's easy to understand, it's accurate and captures all of them, is that it's like a computer. It's like a normal computer that can perform operations. It's a secure computer. I'll get into that more in my next slides then. So what does a computer have? What are the main two components of it? Computer has some code, which represents what this computer can do. This code might represent some logic, and it has some memory. These are the main two components of every computer. And this code represents some logic, and you can interact with it. For example, if this code is representing something like a banking system, you can transact or interact with this code and trigger a transfer to happen. And then the memory of this computer is storing all the valuable information that we care about, such as how much money I have, how much money Nikos has, and how much money each and every one of you has. And really, again, a blockchain can also be represented as the same thing. And the main sort of like value of then this computer versus my MacBook that's sitting on my desk is that the code that runs on this blockchain computer, we can be very, very sure based on assumptions of science and mathematics that it is correct. This computer has some code, you give it some input, it exactly does what the code does, and you can trust the outcome. This is really what blockchains are and why they're valuable in 3 minutes. A few more terminologies as well that I would just bring here for reference, but again, I won't use them for the rest of this slide myself, is that sometimes we refer to that code as state transition function, that logic of the blockchain. This goes back to the state machine analogy. Or in the Polkadot realm, we like to call this code of the blockchain computer, the runtime of the blockchain. Similarly, that what I'm referring to here as memory, which by the way is persistent memory, as in like in computer memory, when you kill the computer, the memory goes away, but this is like a persistent memory. This memory in blockchain is very often referred to as the state, where all the information that the blockchain cares about is stored. But again, for the sake of simplicity and being sort of accurate, I would stick to the keywords of code and memory for the rest of this presentation. Okay, this was a few words about what blockchains are. And then in order to understand what smart contracts are, we can look at the evolution of blockchain computers. So the first blockchains that were ever created were computers that had a fixed code. You could never change it, ever. And that was just it. So if we look at like Bitcoin as a computer, it has some code that encodes how you should deal with this currency called BTC and some logic that allowed for its transfer. And that was pretty much it. So if Bitcoin is a computer, the only code that it can run is just a transfer of BTC. And a few other extra bits. So some of you might be familiar that Bitcoin actually is a little bit scriptable, but you can't build anything useful with it. And this is really the great thing that Bitcoin did was to prove that building this secure computer is possible, but it didn't really innovate in how we can extend it, how we can make it programmable. And smart contracts are the first way to do that. So a smart contract is the first step toward making this blockchain computer that we have now invented programmable, such that you can build different things on top of it, such that you can upload your own code into it and then interact with it. So the main project that has pioneered this is Ethereum. A lot of you are probably already familiar with it. So if we look at also Ethereum as a computer, as like, a logical computer, what is the code? What is the logic of Ethereum? Maybe for some of you who are already familiar, I'm going to pause here and see if anyone wants to answer. What would be the code of the Ethereum blockchain, assuming it's programmable? Raise your hand or leave it in the comment, please. Some people are saying EVM. Too technical. Let's keep it to the the Bitcoin computer could do one thing: transfer BTC. What does the Ethereum computer, which is programmable, should be able to do? Solidity, bytecode, all kind of correct, but I'm looking for more execute programs. That's good. That's, for example, good. Or run smart contracts. Okay, someone else said that. So what are the things that the Ethereum computer can do then? First, Ethereum computer is very similar to the blockchain, the Bitcoin computer, can manage the transfer of ETH that we know of, because there's this currency in Ethereum called ETH. But what you can also do with the Ethereum computer is you can upload a contract to it. You can upload your own code into it. And then what someone else can do and they can go and interact with that particular code that was uploaded by a user into it. So this is another logic that then the code of the Ethereum computer has. Okay, So let's look at a quick visualization to understand this. I'm going to bring my cursor here so you can also see it. I haven't introduced like this, how the contract is written or what is EVM just yet, but bear with me for a second. If we look at the Ethereum computer, there is like some native code into it that is like whatever is the Ethereum code, whatever is the Ethereum's logic to handle ETH token and so on. But what someone else can do, they can create a contract and compile it to a bytecode that's called EVM and upload it into the Ethereum computer. And then another user can come and actually say, I want to interact with this piece of logic that was just uploaded to Ethereum. Similarly, again, a user can also come and interact with Ethereum itself. So none of the contracts, someone can just come to the Ethereum computer and say, hey, I want to transfer some ETH and make that transfer for me. This doesn't involve any smart contract per se, but it's still an interaction that fits here. Okay, maybe it's a good time to pause if there's any questions so far about this computer analogy that I've described. I will scan the chat for 30 seconds or so, and if not, I'll continue. So the question is, are ETH transfer and smart contract code insertion and execution the only two things that Ethereum does? Really, at the abstract level, yes, it's as simple as that. But then through these smart contracts, of course, people have built an arsenal of other functionalities inside of Ethereum. And of course, I'm simplifying things. Ethereum probably at the protocol level has some things that I'm abstracting over here. But yeah, you can really boil down a smart contract platform into these two functionalities. There's a question about storage fees of smart contracts that comes later. I will describe that toward the end of my presentation. How does gas come into this analogy? Described later again. But it's a good, maybe I can actually talk about it. No, I think at the end it will fit better. Someone said, if the computer is the VM and the code is then question mark, what? Maybe if we can, well, this would be a different mental model, but if the computer is the VM, the code would then be the operating system that runs on it. But I think that's it's a more complicated analogy. Okay, I don't see any other questions, but good engagement there. Let's keep it like this. And now I will continue to the next section. So to summarize, if blockchains are computers that can have some code that executes some logic and some memory that stores the output of that logic, smart contracts are just a way to extend the code and memory of a blockchain computer. And what's nice about, like, you might then at this point say, so what? What's nice about it is going back to what I described in one of the first slides, that what is the novel property of this blockchain computer to begin with? That the code that runs on it is secure. It's like has all these amazing security properties that we can be sure it's executed correctly. And any smart contract that is also added to a blockchain like Ethereum in the same method inherits the same security properties of the parent blockchain to which it is deployed. So if you trust the Ethereum blockchain computer or just the Ethereum blockchain to manage or correctly execute a transfer of ETH, you have all the reasons to believe that the smart contract is also being executed correctly. Okay, stepping a little bit outside of these sort of like analogies and mental models a little bit more concretely. So what is a smart contract? In fact, I could have started my presentation here, but I always like to give this like introductions into like, what's the mental model? So a smart contract is essentially a couple of components. It's some code that is uploaded to a blockchain and then runs inside of that blockchain. When it is uploaded, it is assigned an address. This address is how we can then invoke and reference to it and, call it later. It has some memory or state, as we usually refer to it, And again, the only flaw of this like code memory analogy is that memory in normal computers usually refers to ephemeral memory. But of course, here we're talking about persistent memory. If I store that I have, some ETH in a contract, of course, this data stays there forever. It's not like when someone kills their computer, it gets erased. It's persistent memory. And a little bit of extra detail that you should know is that a smart contract, in fact, is very much like an account on a blockchain. In the same way that an account can hold any currency in that blockchain, the smart contract can also own some money. If it's in the context of Ethereum, it can own some Ethereum ETH balance as part of its logic, and then do something with it later on. In fact, to understand a little bit better how this balance and state, for example, are used, let's look at a few case studies of what are like simple but informative blockchains, smart contracts that are being created out there. So one of the most simple but good idea contracts that one can write is an escrow contract. So I want to transact with Nikos, but I don't trust him for example, the scenario would be that I want to sell something, Nikos would like to buy it, but he doesn't trust me to, for example, deliver him that good that he wanted to buy before sending me the money. And what he can do, he can send the funds to a contract. And this is the escrow contract. And this is where the contract having some balance is actually pretty useful. So the funds are now not controlled by Nikos anymore, and they're controlled by the contract. And the contract logic says if both the buyer, which would in this case be Nikos, and the seller, who's me, come and transact with the contract and say approve, a transaction, for example, is called approve, then the funds are sent to me. But if some time passes and both of us don't approve, the funds are returned to Nikos. This is a very simple use case of a smart contract and how we can also utilize this balance component of a smart contract. There's another example that I'm particularly fond of. I actually searched this a while ago. I didn't find a lot of examples of it, so maybe it's an original idea. When I thought of it for the first time, I was sure this is not an original idea, but maybe it is. I like to call it Web3 roulette. So the way it works is that all of us gather, and there's a smart contract, and we all send some money to the smart contract, and smart contract for some period of time accepts money. So all of these monies are just like stored in the contract. At some point, the contract says, okay, time's up. Now it's roulette time. And what the contract would do is say, okay, one of the people who participate gets nothing back. Everyone else get their money back, plus the person who lost. So a very, how can I say it? Maybe not the most benevolent idea, but I find this to also be a very good use case of what a smart contract can do. And again, the crucial part of this is that all of these codes, all of these logics, like an escrow or this roulette, are things that I could also write in my own computer and say, guys, come, just send a post request to Kian's computer and trust that Kian would run this roulette logic correctly. But you might not want to trust me. But if you deploy the same code to a smart contract platform such as Ethereum, and play the same roulette game there, you can be 100% sure that this logic is executed correctly and you can trust it. Okay, time for questions about the escrow and roulette analogy. Very good question from Robin. But someone can run a malicious code in an Ethereum contract? Absolutely, yes. Like Ethereum is not a angel auditing platform that checks all the contracts to be good code. It just assures whatever is that code executes correctly. Now, if that code says steal everyone's money, Ethereum will execute that correctly. And this is not a flaw, it's the design of the system. Again, like it's the computer analogy. You can upload good code to a computer, you can upload a code that does something right, or upload. What happens more often is that people upload buggy contracts to Ethereum very often. And again, Ethereum is not the savior here to come and fix people's bugs. If a code or a smart contract is buggy, it is buggy, and it's executed with that bug all the time. Another question is, how would the contract select the person who loses the roulette. So randomness, for this, the contract needs access to a secure, unpredictable randomness. And most smart contract platform provide this as a feature. Yeah, I think feature is a good word, as a feature to contracts or their other constituents. So there is usually a good, secure, unpredictable source of randomness present in all blockchains, and you can use that as your sort of random number generator, and then you can build whatever else you want from there. The choice of randomness is pretty important in blockchains, because if you choose it poorly, if you choose it not in an accurate way or in a way that is predictable, people can game it. For example, if you use just the block number as the randomness source, people know the future block numbers because the block number of a blockchain increases sequentially. So they can then try and game the system and enter this roulette at a time where the people that they want to screw loses, or make sure they are never the loser of the roulette and such games. So it's very important to have good randomness in blockchains. Is it possible to elaborate on the contracting component of this blockchain-based code execution? Why contract? So if the question is why the terminology is used as a contract, actually, I haven't thought of it. I think it's someone chose the name back in the Ethereum days. The keyword smart contract was chosen as a feature name. I think the word contract fits because it's a contract. This code happens as it is described. I personally dislike the word smart in it because, again, you can upload a very dumb smart contract as well, and then you see, I'm saying dumb smart contract doesn't make sense. I would call it something like secure contract or something, or just contract. Escrow-wise, once the money is in the contract and the buyer got the thing, what if the buyer doesn't approve? Yes. So actually, this escrow contract I described does have a requirement, we can even call it flaw, that I skipped over for simplicity. And this is a very good question. The person who asked this kind of figured out that flaw in that how can the contract know that, Nikas and I exchanged a Rolex watch in the real world, and it cannot in an easy way do that. This is referred to as the oracle problem in blockchains in general. It's not exclusive to smart contracts, but it's a problem that the blockchain code cannot inspect the real world in any native way and know if, again, some exchange happened in the real world, or if some piece of land exists in the real world, and so on and so forth. There are solutions to this, but for the sake of simplicity, I abstracted over them. You can look into Chainlink or other solutions in the blockchain space that claim to be an oracle. General term for this problem is the oracle problem. I think someone answered that theoretically a contract could be written unfairly. Yes, absolutely. A contract can be malicious. Again, and the role of this smart contract platform is not to make it be honest. The role of the smart contract platform is to execute the contract as it is written. Can everyone review the contract code? Yes. And actually, that's a very, very important property of keeping this whole global computer secure. So when a contract code is uploaded to Ethereum, for example, there are tools that allow you to decompile that sort of jumbled computer code into the human readable version, which we call Solidity. I will get to it in my next slide, actually. The programming languages that's used in Ethereum is called Solidity. So you can always decompile a compiled Solidity code into the Solidity code, and you can then read it and check, okay, is this a fair roulette, and do I want to participate in it or not? And if you find a bug in it, you will, or if you find a unfairness in it, you will simply not participate. This is the same security principle that the open source software space generally pursues, that the best security is no security, as in the best way to have a secure system is to have no walls around it, so everyone can see everything. And then we would hope that people would find all of such malicious behaviors or buggy code. And in practice, this works really well. Again, if you look at the number of security flaws that have been found in Linux as a completely open source operating system versus Windows, which is closed source for decades, and I think today it still mostly is. I don't think Windows is particularly has done better because it has always been closed source. People managed to still find severe flaws in that, but Linux actually did better because it was always open source. So anyone could come and read the code and find a problem in it. Yes, someone mentioned code is law. I think this is a keyword that is thrown around. If the code is open source and deployed on a regular server, would it offer similar guarantees as deploying a smart contract on a blockchain network? So I'm assuming maybe this is a blockchain. This is a question that's asked to get me to repeat the point. That the answer is no, because again, if I claim to you that so someone is saying if the code is open source, yeah. So let's go to the roulette analogy again. I might come and show you this roulette code and say, look, this is the code I'm running on my server, trust me. And you verify the code and you're like, right. But unless if I give you access to my server, literally, you will have no way to trust me that I'm actually running the same thing on my server. And especially when it comes to like very critical applications, such as, the Bitcoin currency that is like, trillions of dollars, or Ethereum currency, which is hundreds of billions of dollars, these properties would then be very important for you to be able to trust and have no, like a good way to say it is that there should be no human-based trust in the system. There should be no trust me bro in this process. And in the smart contract version, there is no trust me bro. It's only I trust Ethereum, so it's all good. But in any other scenario, there is at least a little bit of trust me bro. Okay, someone mentioned VRF. I think I'm quite behind the last question, so I hope I can breeze through them quickly. Someone mentioned we have to trust the data providers and Oracle. So oracles are something that, as I said, there are solutions for it out there, but I didn't explicitly say there are great solutions to them out there. A lot of them have trust assumptions. That's correct. But there might be very good solutions to it as well that I'm not familiar with per se, but so someone mentioned that a malicious smart contract can only mess with its own logic and its own funds, and that's correct. Like a malicious contract cannot go and steal ETH from the neighboring contract. That is taken care of, or that much the Ethereum computer does actually guarantee. How can I deploy and create and deploy my smart contract? This is a practical question. There's a million guides for it out there. Someone posted an answer already. Okay, great questions, but let's continue. I don't have too many slides left, so it's okay to spend time on these questions, and I'm enjoying them. But let's continue a little bit further, and then I'll come back to the chat again in a little bit. Okay, how to write a contract. I think we covered these things throughout the speech already, but the language that is used in Ethereum, at least, and it's pretty much the standard for a majority of the ecosystem, is called Solidity. When you see a file with the postfix.sol or file extension.sol, it's Solidity. There are other languages out there though as well that I'm not covering here because again, I want this lecture to be high level. But if you search like or go to talk to your ChatGPT about like various languages, there's more examples out there. But Solidity is pretty much it's kind of like the JavaScript of Web3. It's the language that is not perfect, but it was first, so it has the most adoption. I think the most notable alternatives are what Solana does. So Solana is primarily not Solidity compatible, and they have their own language and so on, but they still have a fair bit of traction. And again, a part of the Ethereum's original code is a logic that says execute Solidity contracts. And how it does that is through a virtual machine called the EVM, Ethereum Virtual Machine. So the flow, maybe I can go back to this diagram and then kind of complete it again, focusing on this first part of it. You have the contract as like written text in the Solidity language, and then you compile this into EVM, which is some bytecode, so not really human readable anymore. And this EVM bytecode is what you would then upload to Ethereum as your contract. A little bit of side note, the outcome of this compilation is not just the bytecode, there's also some, let's call it metadata that helps users interact with these contracts. For example, like you can imagine a JSON file that describes, okay, this bytecode has 3 entry points like transfer, escrow, approve, or play roulette, whatever. So users who want to then interact with this contract later know what are the options that I have available, what are the entry points of this contract. And we usually, in the Ethereum world, this is called ABI, Application Binary Interface. Okay, so this was just a few words about how to write a contract. Now let's look at the other side of this coin, how to execute a contract. So if you are Ethereum, what challenges you have in executing these contracts? So one is that Ethereum doesn't know any of these contract codes. It doesn't know what they are. It doesn't know how much resources, computation they're going to take. So how can Ethereum know that when it wants to give time to execute a contract, this thing is not going to take forever? And the answer to this is this concept of gas and metering that was mentioned in the previous, in one of the chats. So I will talk a little bit more about that in the next slide. For now, what you should know is that a contract, in order for the parent blockchain to execute it, must have a deterministic cost to it. Like you should know before calling into this contract that it's going to only consume this much resources. Furthermore, it has to have deterministic output as well, as in it cannot be that in the blockchain network, Alice runs a contract and it outputs one thing, and Bob executes a contract at the same time and it outputs something else. It must be deterministic. And this is something that's guaranteed by EVM. We don't need to really worry about it. EVM is a deterministic by nature virtual machine. Any code that can be compiled to EVM is deterministic out of the box. So a little bit more about this gas thingy. This is pretty important. The ability for the host blockchain, so I can formulate as this. The host blockchain, when it wants to execute a contract, it should have an ability to measure the cost of that computation as it is progressing. And this is referred to as gas and gas metering. Gas is the unit of that computation, the cost of that computation, and metering is the act of checking it periodically to make sure a contract didn't surpass the amount of gas that was provided to it. And this is why when you interact with any contract in Ethereum or other EVM compatible blockchains, you always have to provide this thing called gas limit, which is both a representation of how much transaction fee you're willing to pay, but also a representation of how much resources this contract that you're interacting with is going to take from Ethereum or the blockchain that is running it. And again, this is very, very important. And if you have a hard time understanding why, go back to that example of how can Ethereum trust this code? How can Ethereum know this contract is not an infinite loop, right? We need a way to tackle this, and the answer is gas and metering. It is also worth noting that this gas notion or this metering notion is not just about computation time, it's also about the amount of memory or state that this contract is consuming. So again, imagine a malicious contract that every time you call it, creates a lot of information, creates a lot of, just fragments the memory, puts random data in there, whatever. There are mechanisms in smart contract platforms to tackle this, and usually it's either part of your gas or it's in the form of a deposit or something that's referred to as a state rent. So every time a contract wants to create some new item in the blockchain memory, which is also in its own memory, it has to also take that into account into the gas cost. And the user, of course, has to pay for it. Sometimes contracts can also subsidize this, so for example, cover the cost, but in principle, it's part of the gas price that is taken into account. Okay, I have two more like miscellaneous properties of blockchains that contract codes that are also worth noting, and then I go back to the questions again. Two other properties of contracts would be that their execution is always atomic, in that if a contract is being called, and then this contract has a long logic that it's happening, and at some point it reaches an error. If an error is occurred, the whole thing is rolled back, and any state change is also rolled back, crucially. Because you can imagine there might be cases where, it's a simple, it's a simple like contract that's representing it like a balance transfer. It cannot be that the contract already executes the transfer, but then realizes, oh, there's, for example, the recipient account was not eligible for this transfer and then fail, but then the transfer already happened. So by default, contracts, in order to mitigate this, they're always written or the virtual machine is always implemented in an atomic way, meaning that either the whole execution of a contract call succeeds, or the whole thing fails and everything is rolled back. Finally, another property of contracts, again, going back to that escrow and roulette analogy, is that contract codes are by definition immutable, meaning that you can never change them once you upload them. And this might sound a bit dogmatic at first, but it comes from for a good reason. And again, it goes back to that trust analogy. So let's imagine it's the roulette contract. I go and read it today and I'm like, yeah, this is a good roulette. I would like to play this. The contract owner should not be able to then come tomorrow and change the code and put something malicious in it and screw me over. So contracts are always immutable. So once you interact with one, once you verify one of them that this is a good contract, I trust it, I want to interact with it, you can trust that it will never change. This poses some headache for the case of what if it has a bug, or what if we want to upgrade that contract? I mean, sometimes there's a benevolent upgrade coming that's making the contract more performant. What do we do with this? And there's programming techniques in the Solidity realm to mitigate this. Again, you can find these things with some search, but I won't go into them here for the sake of time. Okay. Again, questions. This time I'm going to start with bottom because I think I missed some of the chat. So I'm going to start with bottom and answer a couple of questions. Once a user triggers a call on a contract, the miner, how they determine which contract want to execute first. Okay, this is outside of the scope of what I'm describing here. Contract calls are very much like normal operations on a blockchain, and miners typically optimize for profit, which means at some point the miner wants to produce a block in this blockchain, and it has a pool of like contracts calls and ETH transfers and so on to choose from and include this in the next blocks. Usually what they do is that they pick the ones that yield the most profit to the miners in form of transaction fee. But there is a lot of more detail there. Like if you look into the whole MEV realm and sandwich attacks, and when you have DeFi applications, there is a lot of hairy stuff there that I would not get into, but the simple answer is profit. Profit in the form of transaction fee. Can a contract be turned off if the owner wants to shut it down? Yes, contracts can have like a destruct function, which means just like erase me, or I'm not going to be functioning anymore. You can also imagine like a contract has some logic, but all of the logics are gated by if not self-destructed, and at some point someone can, or maybe there's a logic that says the owner can come and destroy the contract. Someone mentioned, if the rolling the state back, isn't this inefficient? Can't we do some kind of dry run execution to mitigate this? I mean, on the user side, you can, of course, always dry run, and before you send a transaction, make sure that your transaction is correct before sending it. But imagine from the perspective of the blockchain and its miners and validators, what can you do? What dry run can you do? I mean, if you want to dry run the thing, you've already executed and you already, wasted some time doing it. So you prefer not doing that from your side. Someone mentioned a concept called a proxy contract. I think this is when I was talking about immutability. Yes, one of the patterns that's used for making contracts upgradable is called the proxy contract. When people deploy two contracts, all the logic is in one contract, and there's a parent contract that only has the interfaces. And the parent contract links to the or uses the implementation contract as the actual logic. And at some point, the parent contract can say, hey, I moved from implementation contract v1 to implementation contract v2, and so on. Someone mentioned something about, please explain PVM and JAM. So PVM, I talk a little bit about it in my final section that comes next. JAM would be very out of scope, but if there's time at the end, I'm happy to talk about it. Please raise it again at the very end of the presentation. How can I test my smart contract before deploying it? Oh, there's an arsenal of testing tools out there, so you can always deploy and run your contract locally. So just on your machine, test it. There's also test networks. So if you want a little bit of a broader testing situation, you can deploy it to a test network where there's no real value. If you screw it up, it's fine. You can just deploy another contract and so on. But there are testing mechanisms out there. Someone mentioned I accidentally killed it. This is a reference to one of the very old flaws in the smart contract that was actually managed by Parity in the days that it was working on Ethereum. There was a multi-sig contract, and it had a self-destruct call, and it was, as far as I know, not protected. So anyone could call it and destroy this contract. And someone actually found this and did it, and a lot of funds were locked then in that contract that was destroyed. Okay, thank you for questions again. Let's continue to the last part of the slide. I was not expecting this, but I think we're going to be very neatly on time, as in I'll finish like 10 minutes in like a few minutes, and then we have this last segment for final Q&As. So a few words about smart contracts in Polkadot and what is the history there and so on. So first, what is Polkadot? I don't really want to explain this here all that much because it's not the purpose of this lecture, and you'll learn it later as part of the curriculum of PBA-X, I am sure. But what you should just know is that if Ethereum was a computer that could run smart contracts, Polkadot is a computer that can run other blockchains. That much I can share right now. And just to sort of like describe the history of the technology, it's worth noting that Polkadot, up until very recently, never considered to deliver smart contracts natively itself, because Polkadot could run other blockchains, and it always assumed that this other blockchain would deliver smart contract functionality. So smart contracts native to Polkadot were not a thing since the genesis of Polkadot until very recently. But just for reference, I have a lot of keywords here and I have links to them so you can go read about them. I just want to like iterate on some of the technologies that are created around Polkadot, in Polkadot around smart contracts, namely for these other blockchains running on Polkadot to then have smart contracts within themselves. So first point is that Polkadot itself uses WebAssembly for its own code and the code of these other blockchains that run on top of it. Therefore, it also experimented with contracts written in WebAssembly and not EVM. And some of our previous technology stack is centered around that. So this like experiment to see if we can have a WebAssembly smart contract actually was successful. And the outcome of it was two pieces of technology. One of them is more like on the implementation low level. It's called pallet contracts. It's a module that you can add to a Polkadot chain that can then run WebAssembly contracts for you. And then we also developed a language based on Rust that can compile to WebAssembly, and you can write smart contracts with it. It is called Ink. And it's still a community maintained project, and it's out there, and you have a link to it in the slide. You can go check it out. Also, Polkadot had, the Polkadot technology stack always had the ability to run EVM contracts as well. This was in another module of the Polkadot SDK called Pallet EVM. And there were a number of blockchains created on top of Polkadot. We call these blockchains parachains, by the way, that were EVM compatible, and they used this Pallet EVM. And finally, coming to where the technology is right now, is that first we have sort of, oh, not we, I would say, the big brains of Polkadot compiler technology stack have experimented with new virtual machines, and they have sort of invented a new one, which is based on, or very close to RISC-V, and it's called PokaVM. This is a much better choice than WebAssembly for a number of reasons that I won't go into them right now, but if you click on the link that is on my slide here, you will find a very long forum post about it as to why this PokaVM is a much better choice than WebAssembly. Maybe I can just name one thing. WebAssembly, unlike EVM, was not very easy to meter. So metering the execution as it's happening was actually kind of difficult, and PokaVM has metering abilities. And then finally, they also created a new module that in Polkadot SDK, we call these modules pallets, that can run PokaVM contracts, and this is called Pallet Revive. I actually don't have it on the slides. I think I forgot about it. And then finally, the last piece of tech that we have invented in the last year is a compiler that can compile Solidity to PokaVM. So putting all of these together, what you can do is now you can have Solidity contracts that get executed by our PokaVM and inherit the faster, better properties of PokaVM. And that's where we are right now. And finally, a sort of community-driven decision that was enacted, I think, about a year ago, and it's still ongoing, is to also add this PokaVM-based smart contracts that are still Solidity compatible to Polkadot itself. So we are currently actually working on this. This is our main sort of task at hand at Parity to deliver, and Polkadot will natively have smart contracts. Hopefully by mid of this year, first Kusama and then Polkadot. And again, these contracts will be executed in PokaVM, but they can be written in Solidity or any other language that can in fact be compiled to PokaVM. But Solidity compatibility is the most important part of it. Okay, final outro thoughts. Smart contracts, going back into the definition of what they are the most simple way to extend the logic or the code of a secure blockchain and inherit all of that security as well. And they are a simple but very good choice for those who want to build anything on top of a blockchain. So nowadays there is a lot of interest in building something analogous to what Polkadot had for a couple of years now called Parachain. In the Ethereum world, it's called L2s or your own rollups and so on, all of which basically boil down to, hey, you have an idea and you want to build it on a blockchain computer, go build your own blockchain. Whereas if your idea is simple enough to be written as a smart contract, it's a very wise choice to actually write it as a smart contract because it's simple and it's battle tested. People have been writing contracts for well over a decade now, and there is tons of resources about how to do every step of the way. It's way more, foolproof. You can't shoot yourself in the foot, so on and so forth. And that's it. Let's go to the question sections. If there's nothing from the organizers, Erin or Nikos, they want to add, I would continue with for the rest of my time trying to answer a question. Does that sound good?
Yeah, go ahead, Kian. Thanks.
Okay. All right. So unfortunately, again, I lost where. Okay, I actually know where I was in the last. Does it make sense to think of Polkadot as the internet of blockchains? Yes, well, you can think of it that way. Yeah, internet of blockchains. In the analogy of today's lecture, it would be a blockchain computer that can run other blockchain computers on top of it. And of course, they're then interconnected. Maybe another analogy that is used and you might resonate with is a like a multi-core CPU. So a CPU that has a lot of threads available, and then it can give these threads to different blockchains to be executed on top of. And of course, when you're running on the same CPU, you have access to some shared memory and so on. I've heard that PVM doesn't require gas metering. I think that's maybe misread or misheard. It's that it's exactly the opposite. PVM allows gas metering to happen easily. So it simplifies a lot of things that we had to deal with in the past, which I rather not go into right now. But the fact that WebAssembly was not easily metered was a big problem for us in the last few years. Does PokerVM still use WebAssembly or not anymore? They would be then no. PVM and WebAssembly are at the same level of stack, so it's an alternative to WebAssembly. You can think of it that way. Can Polkadot run any blockchain written in any programming languages? Yes, Polkadot can run any blockchain that is represented by a WebAssembly bytecode. So any language that can be compiled to WebAssembly, which is pretty much any language these days, can execute on Polkadot. ETH runtime is yes.
Sorry for interrupting. I think
No
there is
worries.
a small confusion for the students, and I read it in the questions between PVM, WASM, and Frame. So it would be nice if you can give an explanation of difference between WASM, PVM, and Frame, and how these are different about smart contracts or not smart contracts.
Yes. So EVM and PVM and WASM are all virtual machines, meaning that there are some bytecode that, there are machines that can run some bytecode. And then it's a question of, okay, how do you create individual bytecodes for this? So how do you create an EVM bytecode? You write a Solidity code, you give it to a Solidity compiler. That's how it works. For PokerVM, you can use the same Solidity code and compile it now to PokerVM. For WASM, as I said, in principle, you can use a lot of programming languages because a lot of programming languages can compile the WebAssembly these days. WebAssembly is very, very well established in the realm of browsers and serverless web and so on. And Frame, I was trying to avoid sort of like getting into that, but in this last segment, I think it's fine. Frame is a Rust framework that creates that WebAssembly code. It's like a easy way to write a blockchain in WebAssembly. This was actually I realize now this was the question or at least the question that I was about to answer was about the same thing. So ETH runtime environment is EVM, Polkadot is WASM or Frame. I kind of covered this already. Is PokerVM the only VM that can run contracts in Solidity as well as other languages? Not in technical terms, because you can. I'm sure people have created other alternatives languages like Solidity that compile to EVM. And like I wish I had a drawing apparatus available so I could draw a diagram for you here. But imagine the bottom of the stack is the array of different virtual machines, and the top of the stack is the array of languages. And this is like a very interconnected graph. These days people are writing compilers for anything. You can compile language A to virtual machine B, and the opposite. A lot of things can be compiled to one another these days. My question is, what are the areas where a standalone L1, which I can translate as a blockchain, is a better choice than smart contracts? It's a very important question. So first, I think the best way to approach this question is if you are a decision maker, or in a few months, any of you guys want to build a demo of some business, some prototype on the blockchain, start with a contract, and only if you hit a wall, you should then consider, okay, does a blockchain make sense for me? But some of the known walls that people hit, and then if they anticipated, we suggest build your own blockchain, is if you need a lot of throughput So because if you need a lot of throughput, a smart contract is like a shared environment. And you will have less resources available to your contract per se. Another issue is this common problem in smart contracts where you are a good smart contract, but your neighboring smart contract is suddenly super hyped, and this neighboring smart contract causes the fee to go up for everyone. That's another problem. If you want to have control over your data more than what a smart contract platform provides, you would also go with your own blockchain. So if you're part of if you're part of Ethereum, for example, you are subject to the same properties of Ethereum, which is, all the state is public, so on and so forth. If for any reason you're building something like a consortium system, like somewhat closed blockchain, somewhat closed system, where you want some privacy over your data or control over it for regulation reasons, you can choose your own blockchain. And one last one, the list goes on, but one last one that I would talk about is fee payment. So when you are in a smart contract platform, 99% of the time, users of your contract have to pay their fees in the parent blockchain's currency. So anyone that wants to interact with any Ethereum contract needs to hold ETH and spend ETH to interact with anything. If you build your own blockchain, you have complete flexibility on this. You can choose USDT for everything. You can even choose just no fee. 5 transactions per day per account are free. Not saying this is necessarily a great idea, but it's something that can be done. Can I write Polkadot smart contracts in Python or Java? In principle, yes, in that you can, if these languages compile to RISC-V, which I think they do, they would almost certainly also compile to PocaVM. And then, yes, you can do that. Someone mentioned that the last update I delivered, that Polkadot will have native smart contract, would come into a Polkadot parachain called Asset Hub, not the relay chain. And yes, that is correct. So these smart contracts will be added to Polkadot Asset Hub parachain, not the relay chain. An interesting one. Does a contract allow parallel transaction, or does it execute them in a queue? So this is not up to the contract, it's up to the environment in which the contract is executed, which is very often, these miners or validators, these are the guys who are deciding, okay, these 5 contracts need to go into the next block. And some blockchains deploy elegant techniques to then execute these 5 contracts in parallel, or it might be 5 different calls from the same contract and just execute those in parallel and then build a block faster. That being said, it's not an easy task, because then what if the outcome of these 5 contracts that were executed in parallel conflict with one another? What if there's a double spend in between them? By default, everything in blockchains is sequential. Some blockchains deploy elegant techniques to parallelize them. That's the answer.
So, Kian, we're getting to the last 2 or 3 minutes of your session.
Okay.
Just want to give you an opportunity to pick a last question or say anything else before you want to close it out.
Yeah, okay. Good prompt. I see 20 unread messages, so which means there's more questions that I won't be able to get into them. Let's wrap it up here. So maybe there could be a way we can still convey these questions, especially the ones that are not answered already in the chat or by PBA-X staff to me, and I can try and answer them in sync. Otherwise we can wrap it up here. I can't think of any additional closing thoughts. Enjoy the rest of PBA-X, and I hope you have learned something new in this lecture.
Thanks, Kian. Yeah, that's a great prompt. If anybody has a
dying question for Keon that really wants to make sure that you get some answers from him, go ahead and leave it in the blockchain Discord room, and we can send those to him, and he can get those to us, get the answers to us in his due time. Otherwise, the TAs can also take a moment to answer them as well. So thank you so much, Keon. As always, it's been so wonderful to have you. We're super excited. You'll be seeing more of Keon content, I believe, further along in the PBA-X course. So pay attention next week in the SCK course. You'll be seeing his face sometimes. Great. And if anybody has any questions, Discord's the place. Otherwise, we have an amazing lecture tomorrow by Bill Laboon from the Web3 Foundation about what's possible with blockchains. So super excited about that. He's actually a trained professor, so he should be really great. Please join us for that as well if you can. Yeah, have a great evening, everybody.
Thank you, everyone. Goodbye.
Thanks, Kian.